An interesting topic in statistical research is research on time-to-event models. Sometimes we have observations, random variables, which are measuring time needed or waiting time for one event to happen. These models are prevalent in reliability theory, when actually waiting time is for device to fail. There is also medical interpretation in survival theory, where waiting time is unfortunately waiting for patient to die or for some event, for example, tumor to grow or tumor to disappear. Essentially, it is just time to event. But it is also applicable to other areas such as geoscience, biology, and there are many contexts in which time to event methodology is applicable. Now, the two main users are reliability theory and survival theory, and they share a lot of methods there. However, they are not really equivalent, although they share many tools, because in reliability theory, you really can do experiments with devices, waiting for them to fail. And for example, you have accelerated testing, accelerated failure, and you can do experiments that you cannot do with people. So although there are some methods which are pretty much shared, in survival theory, you cannot do things that you can do with devices. Let's see first the basic notions of the lifetime distributions. We are going to denote with t random variable, which is lifetime. This is time to event. Of course, t is non-negative. The CDF, standard CDF, is probability that t, capital T, is less than small t. It's f of t. And typical for this lifetime distribution is survival function. It is simply complement to CDF, 1 minus CDF. And that represents the probability that lifetime exceeds specified time t. F of t, small f of t, is density of t. Of course, you know that density is derivative of the CDF, but also it is connected with survival because survival is 1 minus CDF, so it is negative derivative of the S of t. The probability that lifetime is between A and B, constants A and B, is in terms of CDF f of B minus f of A, standard notation, standard result. But in terms of survival function, this is S of A minus S of B. Notice that A and B change the place because exactly of S of t being 1 minus f of t. There is something very typical for lifetime distributions and for this methodology is notion of hazard function. The h of t dt is by definition probability that lifetime is between time t and t plus dt, conditionally that lifetime exceeds t. So in words, that would be probability that maybe device will fail interval t plus delta t, conditionally that this device is working at time t. If you decompose this as conditional probability, that would be ratio in the numerator is s of t minus s of t plus dt, and in denominator is s of t. Well, if you divide this by dt and let dt to go to 0, you really define the notion of the hazard function. The first one, s of t minus s of t plus dt over dt, is negative derivative of s of t divided by s of t. So that is hazard function. Or if you have negative derivative of a function divided by that function, this is simply negative logarithm of that function derivative. So h of t is negative s of t prime over s of t, but s of t prime is negative density. So the hazard function is traditional density divided by survival function. So here I'm going to draw your attention on the difference between the density and hazard. The density, f of t dt, is by definition probability that t is between small t, and this should be small t, and t plus dt, while the hazard is the same probability, but conditionally, that capital T is bigger than small t. As with CDF, which is integral of density, you can cumulate or integrate the hazard function. So cumulative hazard, capital H of t, is integral between 0 and t, h of u du. And that can be represented by algebraic connections that we already discussed, as, for example, negative logarithm of s of t. That is h of t. And then you can represent the survival function, s of t, as e to the negative cumulative hazard. In the context of reliability or survival theory, s of t and h of t are the most popular summaries, s of t being survival function, 1 minus CDF for t, and h of t being hazard function. Now, one notion is very typical in general for time-to-event methodology. That notion is that you are maybe running an experiment, waiting for the event to happen, but for different reasons, you have to stop the experiment, and not all events happened. So you may have sensor data. In this schematic, you have 5 devices. You started running them. Device 1, 2, and 4 failed, and you observed lifetime. However, device 3 and device 5 did not fail, and you had to stop the experiment. So capital C here is censoring time. You may have here censoring indicator, and censoring indicator is 0 if there is no censoring, you have observed data, and 1 if your datum is censored. So in this case, Y1, 2, and 4 will have censoring indicator 0, no censoring, fully observed, and Y3 and Y5, they are censored and they have censoring indicator 1. Typical for most of the experiments are right sensor data. Well, you start the experiment and at some point you have to stop it. And the stopping time implies that you have some sensor data from the right-hand side. You may have also censoring from the left-hand side, but these are considerably less frequent than right censoring. As regards the type of censoring, you have 2 types. One type is you decide when to censor, C is fixed, but the number of observations that are censored are then random, or number of observations which are observed are random. The second type is when you fix the number of observations, and then at that time censoring becomes random. You may say, well, I'm going to run an experiment until I observe 5 lifetimes. Or you can say, I may run an experiment until I see 50% failures. That would be censoring of the second type, because you have number of observations fixed, but the censoring time turns out to be random then. The most common in the analysis is the right censoring of type 1. So how to proceed and how to do inference with censored data? Suppose that you have the model. This is likelihood. Y's are distributed as having density f of yi given theta. Theta is a parameter. You have n observations. Well, but k of them are observed, and delta I is equal to 0 for those, and n minus k are not observed, they are censored, so delta I is equal to 1. How the likelihood looks like? Well, it is a product, and you multiply all densities, likelihood functions, for the observed, and take the power 1 minus delta I. That automatically chooses deltas which are 0. For deltas which are 1, the power is 0, and all these are equal to 1. How about sensor data? Well, you put the s of y given theta raised to delta I. That is non-1, different than 1, only for deltas which are equal to 1 and equal to s. This likelihood is s of y given theta, which is essentially saying that yi is bigger than yi. So you did not observe, but you know that this observation yi is bigger than small script yi. Then how to proceed with Bayesian inference about theta? You get this likelihood, you get your prior, then you make traditional or just normal inference.